have both a long dress and a short dress at the same time. So it's an or situation and it's a mutually exclusive situation. So you add these. Add them, that produces an answer of 4 plus 5, or, yeah. Okay, everybody give me a smiley face if this makes sense. This should be reviewed for all of you since nobody indicated a 0, but just give me the smiley face if we are all on the same page right now. Okay, now this is very quickly going to start getting more complicated. Let me introduce you to what we call the slot method by pointing at some stuff in this problem. And in this problem, the way we can figure this out is we can pretend that there is a slot to fill in for each of these possibilities. So notice that we've got a slot to fill in for the shirt. Let me color code this accordingly. This is a slot to fill in for shirts. And then we have another slot to fill in for the pants. And then it's an AND situation. So it's like having a blank that you put the 4 in, another blank that you put the 5 in. And this is the ultimate backbone of this sort of method. Okay, so let's talk about this in general. And then we'll discuss it in regard to these permutation and combination formulas and so on when that's necessary. But here's the basic rundown of the way that the slot method works. And then I'll relate it to the other material that's in our Manhattan GMAT strategy guides and things like that too. Basic rundown of the slot method. Okay, the first thing about this slot method is that this is used when you have an AND situation. In other words, you have to choose one of these and one of these and etc. Okay, because it revolves around multiplication. So there are going to be 3 steps, but we're not going to have to do the 3rd step all the time. Here's the way it works. First step is you create a slot for each decision that you have to make. Okay, so in this problem, which was again extremely basic, we have 2 decisions to make. We have to pick a shirt out of those 4. Then we have to pick a pair of pants out of those 5. And then of those, there are 4 and 5. We fill in the slots. So we multiply. So fill in each slot with the number of options. In other words, how many ways can you fill in that slot? And then you should multiply. Okay, there's going to be a step 4, which we'll get to in a second. But for now, we'll leave step 4 blank. Step 4, in case anybody is forward-thinking, step 4 is going to be in the case where order does not matter, which is, if you're one of these formula users, then this is the same kind of thing as what we call combinations via the permutations. But let me give you an illustration. We're going to come back to this slide in a little bit. Let me give you a quick illustration of what I'm talking about here. All right, let's say you have the following problem. A 5-letter code must be chosen from the letters in the word Florida. No repetition of letters is allowed. How many different such codes are possible? Okay, before we get started with this problem, quick question for you guys. You can go ahead and type in the text box. When you say a 5-letter code, is the order of the letters important in determining the code? What do you think? Yes or no? Go ahead and type in the text box. Does order matter in this type of situation? Okay, we've got a couple of no's. We've got mostly yeses. This is a yes type situation. Order matters. Okay, let's talk about why. And first, let's clarify what order matters means. Okay, let's go back to this page in which we were talking about this. We're going to fill in step 4 later on. But this is for the step for if order doesn't matter. Again, like I promised you, we're going to fill in this step later with actual technique. But first, let's talk about exactly what it means for order to matter and order to not matter. Okay, what order matters means that if you interchange or scramble the elements, the chosen elements, then you get a different outcome. Okay, so let me give you a couple of situations in which order matters and order does not matter. Okay, if you have 3 of 10 contestants are chosen for gold, silver, and bronze medals, in this case, order matters. Because, for instance, if I say Abe, Bob, and Charlie, that's a different outcome from if I said Bob, Charlie, Abe. These are not different. These are not the same outcome. Because remember, we're talking about gold, silver, and bronze. So this outcome where Abe wins the gold, Bob wins the silver, and Steve wins the bronze is different from if this is gold, silver, bronze. Everybody give me a smiley face if you're following what this is, and give me the non-smiley face if you aren't. Okay. A couple of you give me smiley face in the text box. When I say smiley face, there's also an icon that's over there on your left that's clickable. So, I mean, you can put it in a text box if you want, but it might make more sense to just indicate the smiley face over here. Okay, on the other hand, if I have a situation in which 3 of 10 workers are chosen to serve on a committee, and that's all you're told, then order doesn't matter. Because if you choose a committee of Abe, Bob, and Charlie, that is the same outcome this time as Bob, Charlie, and Abe, and any other scramble that you might want to make. So, in other words, in this case, if I scramble the committee, it's still the same committee. If I scramble the people that win these medals, then I have different people winning different medals, and it's no longer the same. So, smiley faces if that makes sense. Okay, so let's do a quick test of this before we go back to the other problem real quick, before the Florida problem. Here's a quick test of your understanding of whether order matters or not. Quick test of your understanding of order matters. Okay, let's say an advertiser wants to pick 5 pages in a symphony program in which to place advertising. Okay, the pages in the program are numbered 1 through 16. Okay, does order matter? Give me a yes or a no in the text box as to whether you think order matters in this case. Still waiting for, okay, we got a split decision here. We've got some people saying yes, some people saying no. Okay. This is why I wanted to use this particular example, because there's an illusion that order matters. It turns out that order does not matter in this problem. And let me tell you why not. The illusion is that it does because the pages are numbered. Right? The fact that you have numbered pages lends the illusion that order is important here. But remember the operative question in here is, the operative question is, if I scramble the elements, do I get a different outcome? That's really what we're asking here. So just consider a particular outcome where you scramble the elements. Okay, if I say the advertiser picks pages 1, 3, 7, 8, and 11 versus the advertiser picks pages 3, 11, 7, 1, and 8, these are not different outcomes. These are exactly the same outcome. Because notice we haven't specified, different ads to go on these different pages. We just said we had to pick 5 pages. So these are the same outcome. Okay, everybody give me a smiley face if that makes sense to you. Give me the non-smiley face if this is confounding to you. Okay, so this is how you tell whether order matters or not. I mean, this is sort of a deceiving question in certain situations, such as this one. Because when you think order in a situation like this one, then you totally start thinking, oh, look, they have page numbers, so order must matter. But in this case, the order doesn't matter because if I scramble the chosen pages, it makes no difference. Okay, also, this is going to get a little bit more complicated in later problems, but let's make sure we're on the same page here. It's also possible for order not to matter within some subsets. Okay, so for instance, let's tweak this problem a little bit. Let's say an advertiser, so same problem, an advertiser wants to pick 5 pages from pages 1 to 16 in a Symphony program. Okay, on 3 of the pages, there will be half-page ads, and then on 2, there will be quarter-page ads. Okay, in this case, here's the situation. In this case, the order of the 3 half pages, the order within the 3 pages chosen for half ads doesn't matter. And then similarly, the order within the 2 pages chosen for quarter ads doesn't matter. But what's important to realize here is that this is not a set of 5 elements in which order doesn't matter at all. This is probably better conceptualized as 2 sets. One set of 3 in which order doesn't matter, and one set of 2 in which order doesn't matter. It is not a set of 5 elements that can all be interchanged. It's an interchangeable set of 3, and it's an interchangeable set of 2. Okay, smiley face, if that makes sense. Any questions in the text box that you might have at this point? Because this is a very important distinction for the problems that are about to follow. Okay, I'm not seeing quite as many smiley faces. If anybody has any questions about this stuff, go ahead and type them into the text box, please. I'll wait a second to see if any of you guys type anything. If not, we'll move on to the Florida problem. I'm seeing a couple of people starting to type. Okay, I'll wait a second to see what is being typed here. Oh yeah, the question is will there be a sample question? There will absolutely be tons and tons and tons of sample questions. So here's the first sample question. A 5-letter code must be chosen from the letters in the word Florida. So when we say order matters, what this means is like the codes, if my code is FLRIA, and if your code is IFALR, those are different. So order matters in this case. So, okay, the question is, what was the answer for the Symphony pages? We'll get to that later. I want to step through these pages. I want to step through these steps real quickly first. These steps for this problem, then we can come back and revisit that problem in a little bit. Create a slot for each decision that you have to make. So here's the steps. The main reason I'm doing this is because we have more room on this page. Create slots for each decision that must be made. Okay, so how many slots are we going to make here? Go ahead and type in the text box. How many decisions have to be made in this problem? We need 5. Right, because 5 slots, because there are 5 decisions, namely each letter of the code. So here are those slots. All right. Now what you do, as written here, is you fill in each slot with a number of options. What numbers go in these slots? How many options are available for each of these? Go ahead and type in the text box. Yeah, okay, so a lot of you guys are filling in some of you guys are just giving me the number for the first slot, but okay, here's your slots, and then your numbers of options are 7, 6, 5, 4, 3. Because what's happening here is that you can't repeat letters, so you have 7 options for the first one, 6 for the second one, 5 for the third, 4 for the fourth, 3 for the fifth, because each time your number of possible options dwindles by 1. Now, here's an important distinction. Here we chose the slots from left to right, but there's no reason we'd really have to do that. If we wanted to, we could totally pick the 4th slot first. You know, if I wanted to pick this letter first, I could do that. There's no reason I can't. And then if I wanted to, I could pick the 3rd letter next. I could pick this next. Then I could pick the following letters in any order I want. I could pick the first letter, then I could pick the last letter, then I could pick the second letter. So the order in which I do these doesn't really make a ton of difference, as long as it's a legitimate order. So this is a very important takeaway here. You don't really have to pick these from left to right. Okay, you don't have to pick things in the given order. And indeed, as we're going to see soon, in many problems, you are better off picking in a different order. Okay, then after we do that, what happens is we multiply. So we multiply the numbers together. All right, here order matters, so we don't need step 4. But which multiplication makes sense to do first here? Go ahead and type in the text box. Like, which numbers would you want to multiply first? Yeah, 5 and 4 or 6 and 5. A couple of you are saying things like 5 and 3, but that's 15. That's not as easy to work with. I mean, it seems that 5 times 4 is 20 is probably the single most friendly possibility here. So that's 20 times 3 is 60, and then we can multiply 60 times 6, which is 360. And then times 7, we would just go ahead and do that in longhand, unless we have an exceptional capability for doing this kind of stuff in our heads, but that's 2,520. Okay, so there are 2,520 possible codes. Okay, there you go. So the reason, for a couple of you who are asking, the reason we haven't quite finished this problem yet is because this is a problem where order does not matter, and there's a fourth step in case order doesn't matter, which we'll have to get back to. This is a problem where the order totally matters, and so we can just do the first 3 steps of the process. Okay, let's do another problem based on this. I'm going to allow you a little bit of time after I put it up on the board. Here's the problem. No repetition of letters is allowed. And then there's one more condition going to be imposed here, which is first and last letters of the code must be consonants. Which, if any of you don't call them consonants, I know in some countries they don't call them consonants, these are the ones that are non-vowels. So the consonants in this code are F, L, R, and D, and the vowels are O, I, and A. So here's what I want you to do. I'm going to give you a little bit of time. You'll probably have more time than you'll need because I'm going to go run and take a bathroom break real quick. But it'll be about 2 minutes. Solve the problem. But then since everybody sees the text box, wait to type your answers until I'm back. Okay, so I'll give you guys about 2 minutes or so to work on this. Give it a shot. Okay, let's go ahead and get started again. Go ahead and type your answers into the text box, please. And remember that you would actually want to be calculating these things. Okay, so we've got a few different answers being typed into the text box. The consensus answer seems to be 720, and indeed that's the correct answer. Let's go ahead and do a quick discussion of why. Okay, again, step 1 was to create a slot for each decision. Okay, those slots, here's the slots. 1 slot for each decision, 5 decisions. Then you got to fill in the slots with the numbers of options. Okay, and I'm going to go ahead and make 2 sets of slots because I'm going to illustrate the wrong way to do this, and I'm going to illustrate the right way to do it. So, okay, the wrong way to do this, and again, before I even type it, I'm just going to go ahead and type, this is wrong. If you write a 7 here, this is wrong. Okay, already. It's not wrong to say there are 7 letters that could go in this slot. Oh, sorry, it is wrong to say that. My bad. It's a mistake. I mean, of course that's wrong. There's only 4. But let me give you the wrong way to do this. The wrong way to do this, another very wrong way to do this, sorry for a misunderstanding, is to type a 4 here and to type a 6 here. That you can't do. Okay, in and of themselves, these are not lies. But, I mean, there really are 4 letters that could go here. And then once you've chosen this consonant, because there are only 4 consonants, once you've chosen this, there really are 6 letters left over. But there's a problem. Here's the problem. The problem is if you choose this letter, as soon as you've chosen that one, there's now this uncertainty about that last blank. Okay, we don't know whether this is a vowel or a consonant. So it's now impossible to fill in the last blank. Okay, so what you've got to do is you've got to be really, really careful here. You've got to fill in these blanks in an order such that you've got the actual same numbers all the time. This is the importance of this last takeaway. A lot of the time you're better off picking in a different order, and in some cases you will have to. Okay, so there's an important takeaway here, which is this. Let me go ahead and type it at the bottom of the screen. Takeaway is you absolutely must pick the elements in an order such that the numbers of options are always the same. Okay, in other words, if this, like if I pick a consonant here and a consonant here and a vowel here, there's only going to be 1 consonant left over. So this would be a 1. But if these are all 3 vowels, this one, and this one, then there'll still be 3 consonants left over. So that means that there's basically going to be a big fat question mark. So everybody type in the text box, in the correct way to do this problem, which slots do you have to pick first? Yeah, you've got to pick the restricted slots first so that you'll know how many options there are. So you've got to pick this. This has to be a consonant, and this has to be another consonant. So there's 4 possibilities here, and there are 3 possibilities here. After you pick those, then you just have 5 letters left, and now I don't care whether those 5 letters are vowels or consonants. So once I'm in that situation, I can just pick those. So, but in this case, if you try picking from left to right, you're just not going to get it to work. This has to be the first pick right here, and then this has to be the second pick right here. Okay, does anybody have any questions about this? Give me a smiley face. If you don't, we do have to I guess we do have to multiply these numbers. So let's just do that real quick. Then I'll call for the smiley faces again. So third step, you got to multiply. So 4 times 5 times 3, you should probably do first, is 60. And then you still have a 4 and a 3 left over. So 60 times 12 equals 720. So there are 720 possibilities. Okay, so again, smiley faces if this makes sense to you so far, and questions in the text box if it doesn't make sense. You can do problems like these with the formulas, and if we have enough time left at the end of the study hall, I'll go into how to use them. But notice that this approach is pretty simple, and if you could use what are called permutation formulas here, but it's so much more work than what you're doing here. In fact, in problems where order does matter, it's really a waste of time to use permutation formula. You can just use the slot method instead. And we can get into that if we have time, but okay. let's look at another variation on this, and now we're going to discover what this fourth step is going to be. What do you do if order doesn't matter? So, sorry, let's see these problems. Okay, now let's look at this. Okay, let's say that you are to choose a set of 5 letters from the letters in Florida. Again, no repetition. Okay, how many such sets are possible? Okay, first of all, let's type in the text box, what's the difference between a set and a code? Does anybody know? How does this differ from a code? What's the difference between a code and a set? Anybody? If you know, you can go ahead and type in the text box. Okay, a few of you are typing yes. Now it's the order. One thing they do expect you to know on the GMAT is that when they use the word set, the default meaning of the word set is that order does not matter. Okay, this is actually something you are expected to know. So, for instance, if you're to choose a set of 3 integers, then the set 1, 2, 3 is the same as the set 2, 3, 1. This is something you're supposed to know. So, for instance, if you have the set, okay. So if you, for instance, as an example, F, L, R, I, and A, and L, F, R, A, I, these are the same set. Okay, so here's a quick thought experiment. I'm going to go ahead and type it in the text box. In the first problem, in the first Florida problem, you calculated the number of codes in which order mattered. Okay, now we're doing sets in which order doesn't matter. Okay, which number should be greater? Okay, i.e., should there be, oh, you know what? I'm not sending it to you guys. Okay, I need to cut and paste some things. Okay, you should see a bunch of text appearing in your text box right now. Okay, if you give me a smiley face, if you just saw a whole bunch of text pop up in your text box. Okay, good. Smiley faces. All right. So, in other words, should there be more sets or more codes? Go ahead and type in the text box. More sets or more codes? Okay, so we're split almost half-half, it looks like. It looks like for every one person saying there's more codes, there's another person saying there's more sets. Well, let's discuss. So, what's the difference between sets and codes? Okay, well, consider the following. Consider all of these sets. F, L, O, R, I, F, L, O, I, R, F, L, R, I, O, etc., all the way down to I, R, O, L, F. Okay. If these are codes, then they're all considered different. So does anybody know in the text box, this is every single code that's possible from scrambling these 5 letters. Does anybody know how many possibilities there are for doing this? Type in the text box if you know. This is going to be another good takeaway to know. Yeah, it's a factorial. Okay, so this is a separate takeaway. You can actually consider this to be a subset of the SWOT method, but you should definitely know this separately. Important fact, there are n factorial different ways to scramble the elements in a set of n things. Okay, if any of you don't know what a factorial is, this exclamation mark looking deal, if any of you don't know what that is, go ahead and indicate somehow, text box, frowny face, something like that. But this is an important fact. So back to what we're talking about here, if those things are codes, then they're all considered different. And there are 5 factorial, which is 120 of them. Okay, if these are sets, then all of them are the same one set. So there should be way, 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 way more codes. Okay, that's the answer to your thought experiment. There should be many, many more codes because all of these different examples count as different codes, but they're all the same set. So smiley face, if you guys understand that, the number where order matters should be much, much, much larger than when it doesn't. In fact, this is going to be the underpinnings of this rule that you're going to learn. In fact, for every set, there are exactly 5 factorial different codes, since you can scramble the letters. So, in this problem, we figured out the number of codes. The number of codes was 7, 6, 5, 4, 3. This is when the order of everything mattered. So, the number of codes in which order matters was 7 times 6 times 5 times 4 times 3. Therefore, the number of sets, what arithmetic are we going to have to do? Text box, anybody know? If order doesn't matter, what arithmetic will we have to do to find the number of codes? You have to divide. Okay, I mean, some of you are giving me formulas, which is great, but formulas are limited, and we'll talk about why in a second. But you can take the 7 times 6 and times 5 times 4 times 3, and since each of the sets happens 5 different times, you can divide by 5 factorial. So that is going to be how many there are, because you have to divide by this factor. Okay, if you know how to do a combination formula, it will give you the same result, although you will have to simplify a little bit more. Okay, so this is, here's what this will turn out to be. This is 7, 6, 5, 4, 3 over 5, 4, 3, 2, 1. So we can cancel a large amount of stuff here. We can cancel 5, 4, 3. That leaves us with 7 times 6 over 2 times 1. That's just 7 times 3, which is 21 different ways of doing that. Okay, if you use a formula, which I said we'll get to if there's time, then this can work. We're going to look at one more Florida problem, but now let's add step 4 to this. If order doesn't matter, then here's what you do. You take the numbers of items within which order doesn't matter, and then you take the factorial or factorials of those numbers, and then you divide. Okay, and so in this case, there were 5 numbers within which order doesn't matter, and here's the problem right here. You can switch any of them, and so you divide by 5 factorial because there are 5 interchangeable items. So let me go ahead and write that as a little footnote on this formula. It's 5 factorial since there are 5 interchangeable items. Okay. So, I mean, there are also formulas that will do this, but we will see sooner or later that that some of those formulas are limited in scope, which we will talk about in a little bit. Okay. Let's look at one more problem on this Florida thing, and then I'll give you a GMAT problem. Okay. Let's say, let me do some cut and paste. You are now to choose a set of, rather than just 5 consonants, 3 consonants and 2 vowels. Set of 3 consonants and 2 vowels. And again, no repetition. How many such sets are possible? Okay, so go ahead and calculate this. Again, I'll give you about a minute and a half or so to figure this out, and then we'll discuss. So go ahead and figure this out. Please hold your answers until we call for the answer. Thanks. Okay, let's go ahead and get answers that you might have. It's a set of 3 consonants and 2 vowels. We've got some very large numbers, and we've got some small numbers coming up. Yeah, all right, mostly 12s. Okay, some of you might have used formulas, but again, let's use the slot method. All right, let's use the slot method. Okay, number 1, make slots for each decision. And 2, fill them in with numbers of possibilities. And then 3 is multiply, and then 4 is divide by factorials of the numbers of interchangeable elements. Okay, so here's that. Slots, we've got 5 slots. The numbers of possibilities, well, we have to have a consonant, a consonant, a consonant, a vowel, and a vowel. So, is someone typing to me? Okay, someone's typing messages to someone. Okay, so here's the story. Consonants, there are, what numbers go in the slots for consonants here? So how many consonants are possible? Here, here, here. Go ahead and type in the text box. 4 in the first slot, yeah, 4 in the first slot, 3 in the second slot, 2 in the third. So 4, 3, 2. And then the numbers of vowels, by the same token, are 3 and 2. Okay, I'll go ahead and do that in a different color just to make it clear what's happening here. Now, here's the big question. By what factorial do we divide? So let me remind you of another problem, which is this one. Okay, this is kind of like this one. We had 3 half-page ads. We had 2 quarter-page ads. Within the 3 half-page ads, the order was irrelevant, and within the 2 quarter-page ads, the order was irrelevant. Same thing here. We've got 2 distinctive sets of items. We've got consonants that we can scramble, and we've got vowels that we can scramble. So yeah, a couple of you are typing this in the box already. We've got to consider those to be separate sets of elements. We can't scramble between those. So we actually have to divide by 2 different factorials. We have to divide by a 3 factorial, and then we also have to divide by a 2 factorial. Because there are 2 separate interchangeable sets being chosen. Okay, in fact, if you want, you could even conceive of this, I'm going to put some yellow parentheses here, you can even conceive of this as 2 different problems. And in fact, you could even think of it as picking your consonants separately and picking your vowels separately. Okay, now, what we're going to look at is we're going to look at a GMAT. Let me get smiley faces from you first if this makes sense. Does everybody understand the slots? And does everybody understand why there's a 3 and a 2 down here? Smiley faces if you do. Okay, excellent. So this will reduce to, I'm sure you guys can do the mechanics. This reduces to 12. Okay, here's a problem from the GMATprep software. Give this a shot. I'll give you about 2 minutes and 10 seconds. And again, I will collect answers at the end. Go for it. Okay, timer's timed out. So let me go ahead and give you one of these polling things. Okay, you now have A through E multiple choices available. They're in the top left of your screen. Go ahead and pick an answer, please. Remember, just like the real test, if you don't have an answer, go ahead and pick something. Because remember, on the real test, you can't just sit there and look at it. You have to actually pick something. Otherwise, your time will dwindle away. If any of you have been depending up to this point on formulas, by the way, you will probably find that those will crash and burn on this problem. I'm not sure whether you guys can see each other's answers or not, but if you do, then you might just be tempted to pick an answer based on what you see. In any case, I've deliberately refrained from using those formulas so far in this lesson because the formulas they're very difficult to use unless you have a great deal of experience with them. But this is a problem on which you can't really use formulas. And that's the precise reason why I'm pushing the slot method on you guys. Is because formulas only work on problems where you don't really have restrictions imposed on your choices. Okay, so if you normally use the C or P formulas, be aware that those formulas only work on problems where your problems in which your choices are not restricted. Okay, in this case, if you have a restriction, such as 2 people who are married to each other cannot both work cannot both serve on the committee, this is going to render those C and P formulas invalid. All right, you're not going to be able to use them because of this restriction you can't use the formulas. Okay, also, this is your takeaway. Also, the slot method will solve all problems that can be solved by the formulas. So the main reason that I'm not really talking about formulas right now is because you don't really need them. Okay. The only cases on which the formulas are really that necessary is cases where the answers are so big and the numbers of options are so huge that you have to type the formulas into a calculator and get an answer out. But the slot method will always give you the same answers as the formulas will give you. And it'll give you those answers in a much less obnoxious form. Okay, like if we go back to the very first Florida problem, which is this one. Okay, for those of you who don't know, then you don't care. If you use a slot method for this problem, it's just 7 times 6 times 5 times 4 times 3. And that's it, and you're done. If you use a permutation formula, you have to call it 7 factorial over 7 minus 5 factorial, and there's canceling to do, and it's obnoxious, and it's just terrible. So you're better off with the slot method than you are with formulas. And this is not the kind of test that will throw complicated combinatorics at you either. Like, you won't need the formulas. And so just be sure that you can use this sort of method. In any case, let's go through the steps of the slot method. Step 1, make slots for the individual decisions. Okay, how many slots? Go ahead and type in the text box, please. How many slots do we need? Okay, we need 3 slots because there are 3 people being chosen for the committee. So, okay. 3 slots, 3 people. So here's those slots. Step 2 is fill in the slots with the numbers of options. Here's the key. Okay, let's do this one at a time because there are a lot of people with blank answers on this problem. Easy question first. How many options are there for the first slot? Just the first slot. Go ahead and type it in the text box, please. There are 8 options for the first slot. This next thing, this is where the formulas will simply fall flat. It's not going to work. How many options are there for the second slot? There are only 6. Okay, there's not really a formula around that's going to be able to do that for you. Because all of the formulas are going to spit out a 7 next, and there's not a whole lot you can do about it. But it's 6 because once you've chosen this person, you can't pick the same person again, but you also can't pick whoever they're married to. So here's the way it works. Each time you pick someone, that person is disqualified, as is his or her spouse. So you actually lose 2 options every time you make a decision. So therefore, what's the number that goes in the third slot? Text box, please. The number that goes in the third slot is 4. Okay. Then you multiply. So you just insert multiplication signs in between these things. Everybody's happy. But then, this is a committee problem. Okay, if order mattered, you would be done, and the answer to the problem would be 8 times 6 times 4. But this is not a problem where order matters, because this is a committee. So step 4, if order doesn't matter, then divide by the factorials of the interchangeable sets. Okay, so what do we divide by? Text box. Yeah, it's a committee, so there are 3 people being chosen. You can scramble the entire committee is interchangeable. So we have to divide by 3 factorial. Again, the rationale behind this is you ask yourself, and another way to think about that is to think about it as the answer to the following question. And another way to conceptualize this is to think about this as how many identical positions to fill. Same sort of thing. If you think about this as a committee, this is an even more powerful way to pose the question, because the spots on the committee are identical to each other. Whereas if you had something like president, vice president, secretary, and so on, they wouldn't be. So 6 is equal to 3 factorial. Those are the same number. 3 factorial is equal to 6. So therefore, this equals 8 times 4, or 32. The answer is E. Okay. Are there any questions about this problem? If you have questions, go ahead and type them in the text box. Again, you will notice that formulas, for the most part, on a problem like this are a miserable failure. But if you have this slot method, it will quickly dispatch the problem without a lot of thought. As long as you're comfortable doing this. Okay? If any of you are depending on formulas, hopefully this problem is somewhat of a wake-up call. I see a couple of people are typing. So, all right. The question is there another way? There are other ways, but the other ways are all much, much more complicated. It can be done. If we have some time at the end of the study hall, I'll go ahead and show you, but this is by far, like, not even close the best way to do this problem. Like all other ways to do this problem require at least 3 or 4 times as much work as this stuff. I mean, there are ways that in which it can be done, but they're not efficient. So, let me change this up a little bit. I'll leave it on the same screen and see what you guys can do. What's the answer to this problem if the restrictions are the same, but one member of the committee is now chosen as president? All right, so I'll let you think about that for about a minute and change. And I'll put about a minute, I'll give you like a minute 15. You shouldn't need as much time to think about this because it's an offshoot of the same problem. Give this a shot, and I'll check in with you in a second. Okay, let's get answers here. Go ahead and type numbers in the text box. See what kind of thing you guys come up with here. Got only 1 or 2 people with answers. Okay, let's see. Madhu, you were the first person to answer. Do you know how to use the mic? Do you want to jump on the mic at all and talk to us? Do you know how that works? You can tell me in the text box, yes or no. If not, then you can always give us a rundown in the text box. Okay, why don't you jump on? I got to jump off, and then you jump on. Go ahead.
Yeah, my logic in this was that in the original number 8 multiplied by 6 multiplied by 4, and then divided by 2 factorial to get the answer.
Yeah, what changes here is that there are now only 2 interchangeable positions. Okay, there are only 2 positions that can be scrambled now. Because remember that it's only the positions that are interchangeable. Okay, so if you have one person chosen as president, if you want, you can write it like this. I mean, the denominator can also be written as 2 factorial times 1 factorial. But all 3 positions are no longer interchangeable. So this is not dividing by 3 factorial anymore, because there are not 3 interchangeable spots. There are only 2. Whereas the president is unique, and the other 2 members of the committee are interchangeable. Okay, if you want, you can also separate the problem. A couple other ways you can formulate this. You can think about it of this as choose the president, then choose the other 2. In that case, there are 8 ways to choose the president. And then the other 2 are just a 6 and a 4, and they're interchangeable. And then you have a 2 factorial. So you can do that. Remember, it's an and situation. You have to pick a president, and you have to pick the other 2 members of the committee. Also, there's no reason you got to pick the president first. Or you could conceive of this as pick the non-presidential members, and then the president. In that case, the non-presidential members would be 8 times 6 over 2 factorial. And then there would only be 4 people left for president. But in any of these cases, you're going to get the same answer, ultimately speaking, which is 8 times 6 times 4 divided by 2 factorial. So it's going to be 3 times as large as the last answer because there's no 3 in the denominator. So, or as Madhu, I think everybody can see that in the text box. I don't think that was sent as a restricted message. So the other way you could think about this is to get to 32 as before. But then in each of these committees, so like in other words, in each of these possibilities, there are 3 possibilities for this situation. Because when I pick 3 people, I could designate any of those 3 as president. So yes, that totally works. For each one of these situations, there are 3 of these, and so this number should be 3 times as big as this number. The only sort of downside I can think of to that argument is that you would have to do this first. So remember, the GMAT problems are not part A, part B. I mean, if they gave you this problem, then it would be unlikely that you would think of that approach, but it does work. So yeah, it is roundabout. Okay, everybody give me a smiley face if you follow any of these 3 slot method ways to do this last problem. Okay. Now let's do another problem, which can be done. This problem is, I believe, more amenable to things like formulas, but you can also do it with the slot method. So here you go. Give it a shot. This is from gmatprep again. I'll give you about 220. Have a good time. Okay, guys. Answers, please. You got the A through E multiple choices up near your names again. They're up at the top left hand of the screen. They're way up there. go ahead and indicate what your answers are to this problem, please. So if you need like another 10 or 15 seconds, you can take it. But part of the point of the slot method, again, is that it is faster than other methods. So that was already about 2.5 minutes. So see if you can indicate some sort of answer, please. Okay, we still only have about 20% of you guys with answers here. We're now over 3 minutes, so we got to cut the rope here, guys. Go ahead and pick an answer to the problem. Remember, if this is the GMAT, your time is ticking, and if you take this long to answer, you just won't finish the task. Okay, let's have a look. A certain law firm consists of 4 senior partners and 6 junior partners. How many different groups of 3 partners can be formed in which at least one member of the group is a senior partner? So in this case, we can't really do this with a single calculation. Okay, we can try, but it's really not going to happen, because this means that we're going to have multiple possibilities. So this problem has multiple possibilities. Okay, there could be, because there's 3 members of the group, so at least one of them has to be a senior partner, but that's all we know. So you could have a 1 senior partner, 2 juniors. You could have 2 seniors, 1 junior, or you could have 3 seniors, and that's it. So 1 senior, 2 juniors, let's talk about how you would pick that. Again, notice that, does order matter within these people? Type in a text box. Your answer may be more than a couple of words long, but go ahead and type. Among these people, does order matter? 1 senior, 2 juniors. So the full answer is order doesn't matter among the juniors. Or sorry, between. There's 2 of them, so not among, it's between. The full situation here is, note that order doesn't matter between the juniors, but it's not all 3 of them. The 2 juniors. In this case, order doesn't matter between the 2 seniors. And in this case, order doesn't matter at all. So what's the slot method expression for this? Does anybody want to type it into the text box? Well, using the slot method, how do you pick 1 senior and 2 juniors? In the text box, if you get a chance. A couple of people are typing. So you've got some blanks. Remember, you've got to have a blank for each of these choices. So let's do that. 1 senior, 2 juniors. So there's going to be a blank for your senior. Yeah, a couple of people are typing. These blanks are going to be, the first blank is going to be for your senior. And that's too small of a font. The first blank is going to be for a senior. Second 2 blanks are going to be for juniors. Okay, so seniors, there are 4 seniors, and there are 6 juniors. So these possibilities are 4 here, 6 here, and 5. And then remember that order doesn't matter, but only between the two juniors order doesn't matter. So what do we divide this by? Everybody in the text box. Give me some love here in the text box. We divide by 2 factorial, which is, yeah. And if you want, you could call this, you know, or divide by 2 factorial, 1 factorial, if you want. I mean, you can include the 1 factorials. You can say I have 2 interchangeable juniors and 1 interchangeable senior. You can do that. Okay, so that's 465 over 2 factorial. Okay. Now what I'll do is I'm going to drag this. Hold on just a second, guys. I'm going to copy this over here. This is not going to make sense, but you'll see what I'm doing here in a second. Just so I don't have to do as much typing from scratch here. Okay, this is temporarily going to be wrong, so be careful. Okay, now this is still correct, and then the numbers over here now are going to change. So let's kill the numbers. What should the numbers be here? Instead of 465, what should they be? Type in the text box, please. Right, remember again, right now those are the wrong numbers. Okay, yeah. So this time it's a senior, and a junior. So let's edit the numbers that are there. Senior is still 4. The second senior is 3. And now there are 6 juniors to choose from, so that's 6. These are now the correct numbers. And notice that we're still dividing by 2 factorial because there are 2 interchangeable seniors and 1 junior. And then with 3 seniors, this is a little bit more straightforward. 6 seniors to start, or 4 seniors to start with, rather. So we can just do 6, 5, or we can just do 4, 3, 2. And then what is this divided by in the text box? This is divided by 3 factorial. Now, I mean, okay, formulas will work here. I mean, I'll show you that in a little bit. I'll just type. I'm not going to discuss the formulas because, frankly, we're actually already out of time. But still, I want to, like, the main point here, even if you understand the formulas, is you'll just see how much more impressively efficient this method is. 2 factorial is 2, so we can just make this a 2 over here. 4 over 2 is 2. Similarly, again, 4 over 2 is 2. And then 3 times 2 is 3 factorial, so this is a clean cancel over here. Finally, this is an OR problem. So we got to take these numbers and do what with them? Type in the text box, please. What do we have to do with these 3 numbers? We got to add them all up. So when you do this, 2 times 6 times 5 is 10 times 6. That's 60. This is just 6 times 6. That's 36. This is just 4. So final answer we wind up with is 60 plus 36 plus 4, which is 100. There were a lot of people that picked C. I don't really know why, but I have a strong inclination that a lot of you guys picked C just because you saw other people picking C. Because with combinatorics, it's, you know, I mean, otherwise it's kind of hard to get any of them. I mean, a lot of the wrong answers are just sort of random numbers. But, I mean, unless you just did 6 by 4, without doing C. But they're not going to give you problems that But yeah, no, Jorge, you were the only guy I think I saw up there with the correct answer to this thing. So that was nicely done. Okay, again, there are other ways you can do this. Actually, let me show you one other way to do this. In this case, it's not really that much more work than this way. With probability, you may remember, especially if you've gone through our strategy guides and things like that. I'll give you a little bonus solution here because we've spent so much, because I made you so late. With probability, you can subtract from 1 to find the probability of the opposite event. Okay, give me a smiley face if you know about what I'm talking about here. Notice this problem here has nothing to do with probability. This is combinatorics, but still we're going to make a connection. So everybody understands what we're talking about with probability here? Okay, now the difference with combinatorics, you can't subtract from 1, but with combinatorics, you can subtract from what? Does anybody know what you subtract from instead of from 1 if you're doing a combinatorics opposites? Let's see a couple people typing. It won't be from 1 because notice that combinatorics is a number of possibilities. Yeah, we need to find a number of ways where there's no senior, but then the question is, what do we subtract that from? Okay, so we're going to fill this in a second. You can't subtract from 1, guys, because this is combinatorics. I mean, think about what these numbers are. These numbers are numbers of possibilities. These are numbers that are like 60 and 36 and 4. You can't subtract numbers like these from 1. Yeah, Jorge's got this, so we'll talk about this in a second. But in any case, let's calculate the possibilities that you don't want. Possibilities that you don't want. Possibilities that you don't want is all seniors. Sorry, you don't want all juniors. All juniors would be 6 times 5 times 4, and that's going to be 2 factorial. I'll handle that in a second. This is over 3 factorial. All juniors is 6 by 4 divided by 3 factorial. Okay. Now the question is, what do you subtract this from? So again, let me pose the same question. A couple of you typed this, but just to make sure we're on the same page. What goes in this box? Like, here's the possibilities that you don't want. If this were a probability, you would do 1 minus the probability. But yeah, you have to take it away from the total number of possibilities. So right, because this is the same thing. Like with probability, the probability of everything is just 1. But in combinatorics, it's everything minus the ones you don't want. So the ones that everything is 10, 9, 8, and then it's still interchangeable. So you still have to divide by 3 factorial. So that's 3 factorial. And minus that. So if you do these numbers out, then you'll get 10 times 9 times 8 over 3 factorial is 5 times 3 times 8. So that's 120. And then this is 20 over here. So that's still 100. So there you go. Madhu asks, why can't we just do 4, 9, 8 here? In other words, just senior, anybody, and anybody. because the denominators are going to give you a problem here. Right? This is a situation in which you wouldn't know what goes down here. Because if you say 498, then you don't know what you're dividing by. Because if you just take junior, anybody, and anybody, sorry, if you just take senior, anybody, and anybody, then, so like, well, let me address this over here. And then this will be the kind of the last thing that we're talking about today, because we got to cut this pretty soon. Okay. Why? This is one of the wrong solutions. Incorrect solution is to say that it's a junior. Sorry, you need at least one senior. So an incorrect solution is to say senior, senior, actually senior, anyone, and anyone. So, and then if you try to fill those in, this is all good until you get to the denominator. Like this can be a 4, and then this can be a 9, and this can be an 8. If you were picking a senior president, anybody for vice president, and anybody for secretary, this would be exactly correct. But the problem is that that's not what you're doing. The problem is you're picking an interchangeable committee, and so we don't know what the denominator is. The denominator is question mark, because this is 2 factorial in some situations, 3 factorial in others. In fact, as we see exactly which ones it is, it's 2 factorial in these 2 situations, and it's 3 factorial if you pick all seniors. So this won't work because you won't have a common denominator. Again, that's a takeaway I wrote before. You got to make sure that you have consistent numbers. But again, I imagine that a lot of you are probably using formulas and running out of time. And the formulas will work. We don't really have time to discuss that because it's about 8:15 here already, 11:15 over there. So we're over by 10 or 15 minutes. But they work, but they take so much longer. So if any of you guys are addicted to using the formulas, I just want to give you pause a little bit because this problem, you just can't do it. Like this problem, if you throw formulas at it will throw them right back at you. But this problem does take formulas that will take you much longer. Like this one would be what? This one would be 4 factorial over 3 factorial, 1 factorial times 6 factorial over 2 factorial, 4 factorial. Deep breath, that's just one possibility. These ones would be 4 factorial over 2 factorial, 2 factorial times 6 factorial over 5 factorial, 1 factorial. And this would be 4 factorial over 3 factorial, 1 factorial. That's a lot of factorials, guys. So it's better to have this kind of thing at your disposal for a complicated problem. But if you do get a really simple problem, then formulas are probably the best place to go. Like if you know your formulas and you get the floor of the problem, then that's one formula, and you're done. But with problems like this, know your slot method. Okay. Any quick questions before we kill it for the day here? Again, I'm sorry for the initial delays. We will try not to have that happen in future editions of the study hall. Anybody got quick questions for me? A couple people are typing. Thank you. You guys are welcome. All right. So I hope it's been helpful. It's a very intimidating topic, but it's just because the way they give it to you on the GMAT is very different from the way that schools teach this. Like I have a lot of students, I have especially students from India who are very, very, very good at using formulas for this stuff, like amazingly good. They can use them really fast. But, and it must be either it's preparation for that CAT test that they give over there or it's the schooling, I'm not sure. But the problem with the GMAT is that a lot of these things are very unconventional problems, such as this one, on which those formulas will fall flat, even if you know exactly how to use them. So, all right, let's, I know it's one more person typing. We're going to call it a day here pretty soon. Actually, I think it's just somebody having technical difficulties. So let's call it a day. You can go ahead and just quit out of the application. You can just quit if you want. Otherwise, after about 3 or 4 minutes, I'll go ahead and log you out. And I don't know about future study hall scheduling. I'm not sure we've done that yet, but I'm sure we will post announcements if we do. So, and if we do have future study halls, it'll be me again. So I hope you enjoyed it. There is not a study hall next week, no. The study halls are pretty much alternating weeks, but I think they're going to wait until after the holiday season. So just letting you know. But there will be announcements whenever there's going to be another one. Okay. Thank you guys for attending, and have a good night.